Problem 1. Find the zeros or x-intercepts of the function y equals 3x squared minus 2x minus 7. Since this is a calculator problem, we can go ahead and use our calculator to graph it. And if we do so, we end up getting a parabola that looks something like that. And since it asks us to find the zeros, we are going to use the zero feature of your calculator. If you don't remember how to use the zero feature, you can go in my chapter P videos and watch the video about finding zeros on your calculator. But when you do so, when you get this left zero, it will come up to be negative 1.2300, and the right zero is 1.8970. Please remember that you do have to be accurate to 3 decimal places. Number 2, find the point or points of intersection of the functions y equals square root of x plus 5 and y equals 4 minus x squared. Okay, once again, since this is a calculator problem, we'll go ahead and graph the function, and if you do so, you are going to get a parabola opening down, and then you're going to get a line, and you'll notice that they do intersect in 2 places. And I'm going to use the intersect feature of my calculator. We'll have to use it 2 different times to find both of the places of intersection. If you're unfamiliar with how to find the intersect again, you can watch my video in chapter P to help you find that. All right, so when I find this point of intersection, the right point of intersection is going to be 1.227, 2.495, and then the left point of intersection is negative 1.455, 1.883. And please notice again that I am accurate to 3 decimal places. Do not use the trace button at all. Number 3, determine the domain of the function y equals x minus 2 over x squared minus 3x minus 28. Now if you remember, the domain has to do with the x, and it pretty much has to do with what we can or cannot plug in for x. So first thing I like to do, since it's a graphing problem, we can go ahead and graph it. And if we do, we're going to get an asymptote going over here. We get an asymptote over on the left. And this is what my graph looks like. I don't know if yours looks exactly like it, but it should look something like that. Now, some of you, it might be hard to see what's going on with this problem, like is it hitting at 7 or negative 3 or whatever. So I always also do this problem non-calculator. I know there are going to be discontinuities wherever the denominator is equal to 0. So I'm going to figure out, where does the denominator equals 0. This will factor, and it factors as x minus 7 times x plus 4. And if I set it equal to 0, that will occur at x equals 7 and x equals negative 4. So really what I found out is that x cannot equal 7 and x cannot equal negative 4, but it can equal everything else. So to show that it can equal everything else, it can equal anything from negative infinity until I get to negative 4. It can equal anything between negative 4 and 7, and then it can equal anything from 7 all the way up to infinity. And we are using our parentheses instead of brackets to show that we cannot include 7 and negative 4 in our domain. Problem 4, find the limit graphically of x approaching 3 of 2 over x minus 3 to the 5th. Now if you remember, graphically, that means drawing a graph. So we get to use our calculator. So if you draw a graph for this one, this is what the graph will look like. There's an asymptote at 3. And then we've got a graph that's going like that and like that. Whoops, kind of getting closer to that asymptote, of course. Okay, we want to find the limit as x approaches 3. So I want to find the limit as x approaches 3 from the left, and I want to find the limit as x approaches 3 from the right. So as I'm approaching from the left, you'll notice I'm heading towards negative infinity. And then as I'm heading towards the right, I'm heading towards positive infinity, and in order for the limit to exist, the limit from each side has to equal each other. So I will say the limit does not exist. And my justification would be because the limit as x approaches 3 from the left does not equal the limit as x approaches 3 from the right. We do have an asymptote there, but that is not why the limit does not exist. Okay, this next one, it says to find the limit numerically. Numerically means to make a table. So I'm going to now make a table, and again, we get to use our calculator. The table feature of our calculator will work quite nicely. I'm going to do 2.9. No, I'm not. Yes, I am. I'm going to do 2.99. And I'm going to do 2.999, and 3 will be there, but we can't plug in 3 because it will make this problem undefined. And I'll do 3.001, 3.01, and 3.1. So if I plug this into my calculator, please remember to have the numerator in parentheses and the denominator in parentheses. The y value that goes with 2.9 should be 1.16949, and then if I plug in 2.99, it should be 0.16694. And then if I plug in 2.999, I get 0.1666619. 3.001 is 0.16664. 3.01 is 0.16639, and 3.1 is 0.16393. So as I'm coming in from the right and I'm coming in from the left, I notice to 3 places my limit is going to be 0.166. And if you're familiar with the fraction that goes with that, that would be 1/6. Either one of those would be acceptable answers. Okay, problem 6, sketch a graph of the function y equals x minus 3 over x squared minus 9. Don't forget holes and vertical asymptotes. So, first thing that I'm going to check for are holes and asymptotes. I'm going to factor the denominator, and I notice x minus 3 can cancel out. So I know that at x equals 3, since there's a removable discontinuity, there is going to be a hole in my graph. And I also know that at x equals negative 3, because it's a non-removable discontinuity, I will see an asymptote there. So I get to use my calculator, so I'm going to use my calculator. When we do the calculator, we do actually see the asymptote occurring, and the picture looks something like this, I believe. And then coming in from the other way, I might have this backwards just to let you know. I don't remember if I used my calculator incorrectly. So if I have my branches going the wrong way, I apologize in advance, but I don't have a calculator right in front of me to check it. So I do need a hole at 3. So again, it is quite possible that it was supposed to look like this. It might have looked like that and coming up. I really don't know, so don't hold it against me. Alrighty, problem 7. Find A and C so that f is differentiable on the entire real line. In order for something to be differentiable, we have to, first of all, it has to be continuous, and we have to be able to take the derivative. So those are the 2 conditions we are going to be checking. All right, so first of all, I'm going to check continuity, continuous. Okay, in order for a function to be continuous, the limit has to exist. So we're going to check the limit as x approaches negative 3 from the left. Sorry, that should be a negative sign. And we're going to find the limit as x approaches negative 3 from the right, and those 2 have to equal each other in order for this to be continuous. So if I plug negative 3 into the left side, I'll get 2a times negative 3 minus 7, and if I plug negative 3 into the right side, I'll get 4 times negative 3 squared minus negative 3 plus c, and I know those 2 have to equal each other. Simplifying, I'm going to get negative 6a minus 7 equals 39 plus c. Now you'll notice that did not help me find a and c, so I'm going to go to my next step, is I know I have to be able to take the derivative. And if I'm going to be able to take the derivative, if I take the derivative from the left side, so as I'm coming in from negative 3 from the left, it has to equal the derivative as I'm coming into negative 3 from the right side. So we're going to go ahead and do that. Derivative from the right side, the derivative of 2ax minus 7 is 2a. And then the derivative from the right side will be 8x minus 1. But we do know we're approaching negative 3, so I'm going to put negative 3 in for my x, and I'll get negative 25. And I do know that those derivatives have to equal each other. So now notice I can solve for a. So I'm going to get a equals negative 12.5. Now I can go and do a substitution and put a in over here. I'll get negative 6 times negative 12.5 minus 7 equals 39 plus c. And then over here, if I simplify my work, I'm going to get 68 equals 39 plus c. If I subtract 39 from both sides, I will get that c is equal to 29. And I have found a and c, just like it asked me to. Okay, problem 8. Graph a function that meets 2 of the 3 conditions for continuity at x equals 1. Describe which conditions are met and which one is not met. Well, I'm going to, if we're going to meet 2 of them, we really need to meet the first 2. And I'm just going to go ahead and draw what graph I came up with for this one. Okay, this is what my graph looks like. Okay, and I'll just kind of describe. The first thing I would say is that f of 1 is defined, because there's a point there, and actually I'm even going to write that f of 1 is equal to negative 2. It's defined. Okay, second condition would be that the limit exists. So I'm going to say the limit as x approaches 1 exists. And if you're wondering why, the limit as x approaches 1 from the left equals the limit as x approaches 1 from the right. And that limit is equal to, as I'm coming in from the left and I'm coming in from the right, notice I'm getting to a y value of 2. Okay, so that condition is met as well. The third condition is not met because you'll notice f of 1 does not equal the limit. So I can now say that f of 1 does not equal the limit as x approaches 1.